So we saw in the last video that converting to CNF using the multiplying out the brackets transformation can sometimes lead to exponential blow-up in the size of the formula. So in this video, I'm going to talk about a more sophisticated way of translating formulas to CNF called the Tseytin transformation. So this transformation converts a formula into CNF for the most 3 times as many clauses as there were connectives in the original formula. And this is in opposition to the multiplying out the brackets, which can give potentially exponentially many more clauses than there were connectives in the original formula. And the basic idea behind the transformation is that we convert the formula into equations first, so one connective gets translated to one equation, and then we convert each equation into clauses, so one equation becomes 2 or 3 clauses. Now the wrinkle here is that the result is not equivalent in the sense that we looked at last time, but is what is called equisatisfiable. And this will be enough for us to be able to put the formula that results from the Tseytin transformation into a sat solver, and then be able to get any satisfying assignment back from that to the satisfying assignment for the original formula. So step 1 is we take the formula, so this is our example formula here, and then we name all the non-atomic subformulas. So what does this mean? Is, well, we give a name to the top level formula, we call it x1, and the top level formula is something or c. So we're going to say x1 is equal to x2 or c, and then x2 refers to this subformula here. Then x2 is a negation, so x2 is equal to a negation of x3, where x3 is a and another subformula, so x3 is equal to a and x4. x4 is this subformula here, so it's something complicated, x5 or b, and then x5 is just equal to not a. So we've taken the original subformula and we've split it up into this system of equations. And now the idea is to take each one of these equations and represent the fact that this holds itself as a collection of clauses. So how do we do this? So we want some clauses that are true for every valuation that satisfies the equation. So we want it to whenever x is equal to y and z for some valuation, we want the formulas we get from this to be true. So how do we do this? So we derive that by using the multiplying out the brackets idea from before. So we're going to say the formula we want to be true is x equals y and z. So that's the same as x implies y and z implies x. We then convert these using the implies is the same as not or, so we get not or x or y and z, and not y and z or x. And then down here we multiply out the brackets to push this and underneath this or. So we get, to push this or underneath this and, so we get not x or y and not x or z, and then we use De Morgan here to push this not under this and, so he's flipped the and to an or, so we get not y or not z or x. And so this set of clauses here are satisfied exactly when x is equal to y and z. And you can work this out by doing a truth table as well. So if we do this for all the connectives we have, then we end up with these 3 templates for how to convert things. We take each equation, x equals y and some connective z, and turn it into clauses. So we saw that how to do x equals y and z, we turn it into these clauses. If we have x equals y or z, then it's possible to work out that we get these clauses. And if we have x equals not y, then it's possible to work out that we have these clauses. And then finally, if x is the name of the whole formula in our original list of equations, then we add a clause that's just x at the end. And this asserts that our original formula must be true, because we're saying x is true, and then one of these lines will say that x is equal to something else, so that will say that other thing must be true, and so on. It will ripple through the whole system of equations that we've encoded in our clauses. So here's an example. Let's say we take not a and b or b and a. So this is a translation of a and b implies b and a. So we name the subformula. So we have the top level one is x1, which is x2 or x4, because there's an or here. x2 is not x3, so that's this bit over here. x3 is just a and b, and x4 is b and a. And then we turn each one of these into a little collection of clauses according to the lookup table we had on the previous slide. So for instance, x1 equals x2 or x4 becomes this line, and so on for each of the equations. And then at the end, we just assert that x1 is true. And now we can see that if a sat solver using the unit propagation rule goes through this, it will immediately see that x1 must be true. So that will turn this part to be false. And then to make the rest of it work, we either have to make x2 true or x4 true, which corresponds to making one side of these true. So in small examples, it's not really easy to see the benefit of the Tseytin transformation. But the point is that we always get less than 3n clauses, where n is the number of connectives. And multiplying out can result in an exponential number of clauses. And it's also possible to optimize the transformation. And if you look at the tutorial questions, you'll see some examples of that. Now, the little wrinkle is that the formulas generated by the Tseytin transformation are not equivalent to the original in the sense that I talked about in the first video this week. And this is because they have extra atomic propositions. So here's an example. If the original formula was just not A, then the Tseytin transformed version, assuming we don't optimize it, is this. We're going to say x must be true, and then these two clauses here essentially say x is equal to not A, by saying either one of them is true and they can't both be true. Now, the valuation A is false and x is false satisfies the original, because if A is false, then not A is true, so that's a satisfying valuation for this, and it doesn't matter what x is. But this doesn't satisfy the transformed version, because for this one it does matter that x is true. So these formulae are not equivalent, but they are equisatisfiable. So equisatisfiable means that if there exists a valuation that makes one of them true, then there exists a valuation that makes the other one true, and vice versa. And in fact, with the Tseytin transformation, we can go a bit further and say that if we have one that makes the Tseytin transformed formula true, then all we have to do is forget about all the additional xi's we made up for the transformation to get one that makes the original formula true. So if there exists a valuation v that makes the Tseytin transformation transformed formula true, then the valuation v prime, which is v without the additional xi's, makes the original formula true. And because we don't have exact equivalence, we just have this transformation between satisfying valuations, this is called equisatisfiability. The two formulas are satisfiable exactly when each other is satisfiable, but not necessarily with exactly the same valuations. So for our little example, we just have this valuation satisfies not A, but this isn't enough for this because it doesn't mention, for the transformed one, because it doesn't mention x. So the corresponding satisfying valuation for the transformed one is the one where x is true. So A has to be false and x has to be true. And because the Tseytin transformation works by building new clauses from equations, it's always possible to find a satisfying assignment, because we can just start from the satisfying assignment of the original and then work through the equations to work out what the extra variables ought to be. So this shows that if the original formula was satisfiable, then the transformed one is, and if we have any satisfying assignment for the transformed one, then we can convert it back to one for the original formula. So in summary, the Tseytin transformation converts formulas to CNF, and it generates less than 3n clauses where n is the number of connectives, and we can make this a bit better by doing some optimizations as well. But the main point is that it avoids the exponential blow-up inherent in the multiplying out the brackets transformation. And it's important to remember the result is equisatisfiable, not equivalent to the original.